Hello, my name is Adrian Rodriguez, and today we will be discussing using ethers as inhalation anesthetics. To start off, ethers are organic compounds that are composed of an oxygen atom connected to two R groups or substituents, which can be two alkyl groups. An alkyl group is a single bonded carbon and hydrogen atom linked together in a chain of varying lengths. Halogenated ethers will be the focus of this presentation, which is a type of ether that has one or both of its substituents that replace some or all hydrogen atoms with halogens. One example is sevoflurane, where one of its substituents is a carbon bonded to two fluorine atoms and one hydrogen atom. The other substituent is a carbon chain where the second carbon is bonded to three fluorine atoms. One of the most popular uses for halogenated ethers is for anesthesia. Anesthesia is the use of medication to reduce the pain felt by a patient during surgeries or other procedures. Anesthesia can be applied in several ways, such as through injections, inhalation, or both. Anesthesia works by inducing muscle relaxation, unconsciousness, or a loss of sensation. Anesthesia has some drawbacks such as hyperthermia, nausea, vomiting, drop in blood pressure, muscle rigidity, and metabolic imbalances depending on which anesthetic is being used. Through the use of monitoring devices, newer techniques, and generally safer anesthetics, these issues can be minimized, though this level of safety wasn't always around. In history, other compounds were used as inhalation anesthetics, such as chloroform, ethers, or nitric oxide, also known as laughing gas. These early anesthetics had high adverse effects such as nausea, vomiting, lung damage, irritation to the lungs, or suffocation while being under, and etc. This had led to a pursuit of finding more suitable alternatives. In the 1900s, the use of diethyl ethers became popular, but it still had many similar downsides to pre-existing anesthetics. Diethyl ethers is a simple ether that has two ethyl substituents, which is a two carbon chain connected to the center oxygen atom. It was not until the 1970s that halogenated ethers were introduced, such as enflurane, which would then later be replaced by newer and more efficient ethers. One of the most widely used anesthetics in our time is sevoflurane, which became available in the US in 1995. In modern times, inhalation anesthetics that are being commonly used today are nitric oxide, halothane, isoflurane, desflurane, and sevoflurane. These compounds were much safer as they were potent, caused less irritation, and provided quicker recovery time for the patient. However, these anesthetics still had downsides such as drop in blood pressure, irritation of the lungs for people of pre-existing respiratory issues, and a decreased amount of blood being pumped by the heart. Most of these anesthetics are liquid at room temperature, so they are vaporized and mixed with oxygen before they are administered. The gas mixture is then passed through the patient's system by reusing the exhaled gas to maintain a consistent concentration in the body, where it travels from the lungs to the bloodstream. Inhalation anesthetics are also commonly used in combination with other IV anesthetic agents. Dosage of sevoflurane range from 1.4% to 3.3% in oxygen. where the higher percentages of around 3% are for newborns and children of less than 3 years of age. The lower percentages are meant for older adults, where ages around 25 to 40 would require about 2%, and ages of around 60 to 80 years could be dosed around as little as 1.5%. These anesthetics cause their effects by modifying nerve endings in the brain called synapses in some shape or form. These nerve endings have a gap between them called a synaptic gap. When an electric signal is sent, neurotransmitters are then released from one end to the other until they reach and bind to a receptor, creating another electrical signal in the synaptic cell. Neurotransmitters are small organic molecules that have varying roles and uses. The binding of these organic molecules to a receptor would trigger different processes depending on the signal, such as blocking or opening up a process that could release or withhold certain hormones or simply continue to relay a message. In the case of sevoflurane, its effects on inducing and maintaining anesthesia are generally unknown, but research suggests that there is at least 4 main ways. One of them being preventing the release of neurotransmitters from the synaptic cell, stopping the signal altogether. The compound could block the binding sites of neurotransmitters so that they are unable to carry on the message. It can also cause an electric signal to release neurotransmitters, essentially starting or sending a message. The compound can also cause a retake of neurotransmitter back into the synaptic cell, essentially removing the message. We will be going over 2 receptors that are affected by these processes, starting with gamma aminobutyric acid receptors, or GABA for short. These receptors is a type of chlorine channel, and when the GABA receptor is activated, it blocks the activity of GABA A by binding to it, opening up its chlorine channel. A GABA A receptor is in charge of mediating sedative effects from anesthetics or alcohol. Modifying the GABA receptor to prevent its activation allows GABA A receptor to remain closed, thus enhancing neuronal inhibition or decreased neural activity. Another receptor that sevoflurane affects is the glutamine receptor, which is an excitatory neurotransmitter, which means that it excites neurons to fire off a signal to pass a message, and this receptor helps maintain memory, mood regulation, and cognition. Sevoflurane decreases the activity of these receptors by binding to and occupying the binding sites of the receptors on a synaptic cell, blocking most, if not all, neurotransmitters. This process aids in the effectiveness of the anesthetic. And this marks the end of the presentation. Thank you.